Another, a fairly what I think is unique feature of ICM, although I didn't pull it out of the air. I mean, it's got good, it's based on literature studies and this not, so on. So dissolved organic phosphorus, what we call mineralizes to inorganic phosphorus. Now, most models will just have a mineralization rate so much per day, so much % of the DOP mineralizes. What we've got is we actually have a base mineralization rate, but we have an additional rate which oddly enough is proportional to the algal biomass. Okay, and what happens is when there's a shortage of phosphate, algae submit, there's an enzyme, I think it's called alkaline phosphatase. Algae excrete this enzyme, and what it does is it speeds up the mineralization process. Don't take my word for it. Ask Krosten Overbach or Boney and others. You see those references are in the 1980s because that's when I did these kinetics originally. But, you know, this is no joke, it's real. So what we've got here is a function that there's a mineralization rate that is a function of the phytoplankton. And haven't we seen these before? Another rectangular hyperbola. Oh, how many of these can we take? But getting serious, what you see is the way this is formulated is if phosphate is abundant relative to the half saturation constant for phosphorus uptake, this is very small. And what that says is the algae don't need to excrete this enzyme because they have all the phosphate they need. On the other hand, if the available phosphorus is much less than the half saturation constant, this thing approaches unity. And we find that there's an additional mineralization, which is a function of the algal biomass and of this parameter. So, so here you go. This is N, it's not nitrogen, it's the nutrient. And what it says is as the nutrient is gets much greater than the half saturation constant, the mineralization rate, how should I put it? The total mineralization over the minimum approaches unity. There's nothing additional from the phytoplankton. On the other hand, if the nutrient is scarce relative to this half saturation constant, the total mineralization relative to the minimum value increases, okay? So if you have a real shortage of phosphorus relative to the half saturation constant, it's going to mineralize faster, okay? Again, I think this is unique. On the other hand, well, I think it's unique, and we'll stop there. Is there anything else I want to show? Yeah, well, we're going to go over a few other things. Jim, this is interesting. Here is the PIP.
Fraction?
Yeah, well, it's the PIP versus PP in the Susquehanna River. So you can see that, like I said, I think the number's about 40%.
Yeah.
And it's consistent. Look at all that data. It's almost a straight
line.
It's beautiful. You know, the very few points don't fall on that. So, so there's a lot of particulate inorganic phosphorus comes into the bay. And I know when we go way back to our very first bay model, you know, about 1990, we had an enormous shortage of total phosphorus. We could not predict the total phosphorus in the bay, and that's because our first model ignored shoreline erosion. You know, a lot of the total phosphorus comes from shoreline erosion, and a lot of that is this particulate inorganic stuff.
Just again, just kind of quick question. Are there spatial differences in the shoreline erosion in terms of maybe certain areas have more iron in the sediments, or certain areas might be more agricultural, or basically it's a sort of a constant?
We don't have the data to say that.
Okay.
You know, we actually, We don't have the data to say that, but the people in I guess it was at VIMS, they did a really nice measure of the composition of what comes off there. But, you know, there's just not enough to say, just repeat myself, we just don't have the data. So on the average, we can say what it's made of pretty confidently, but that's the size of it.
And so the tributaries, any tributaries that you're modeling, which have shorelines, you also have the erosion in the tribs as well. Okay.
We went to, I don't know if we're going to get to it in these lectures or not, but we went to a great deal of difficulty, I guess in the previous version of the model, to compute shoreline erosion. And we had Jeff Halka, we had a team of specialists who really went at this and computed shoreline erosion to the highest, as best it can be done, which is not necessarily all that good, but at least, you know, the best professionals did the best job possible.
I'm sorry, one last.
Yeah, go ahead.
Just thinking about erosion as being driven by flows, high flows. Again, you may not have the information, but I guess the question is, you said it's constant, so you don't look at increased erosion as a function of, let's say, high flows.
Actually, the watershed team, what we got from Jeff
Halka. I wonder about head of tide would probably have that. That's what the watershed model does. So I'm thinking of your tribs that, you know, that are below head of tide.
What we got from the team, from Jeff Halka, were long-term erosion rates.
Okay.
And what I initially put into the model was a constant. What has happened in this version of the model, they have moved shoreline erosion into the watershed model. And they do that because they want the municipalities to be able to get credits for controlling shoreline erosion.
Okay.
And when it was moved, where's Gopal? Look, there he is. Okay, you're the culprit, Gopal. But I think what you have done is to take that long-term erosion rate and make it a function of runoff.
That's right.
Yeah. So the long-term erosion rate is a function of runoff, and but you know that in the long run it is the long-term rate, but in time it's a function of runoff, and we get that now as a watershed model input. Fair enough?
That's correct.
Okay. Yeah.
Hey, Carl, so in this model you don't have absorption dissorption for you know this PO4, but you still have a settling tone for it due to co-precipitation with iron and manganese.
Okay, yeah. Boy, oh boy, did we? Well, I was wondering what that missing slide was about. Okay, let's go back up one. This is another source of continuing frustration to Carl. For two reasons. Carl is frustrated, number one, because he's frustrated, and he's frustrated because nobody else is frustrated. Let's look at something. This is, you look at the dates on this data. So this was from our very first modeling study. And those X's are, the X's are observations. So what we've got at the top here is dissolved oxygen, and what we've got at the bottom is phosphate. This is phosphate. So the thing I want to look at is what happens with dissolved oxygen is in the summertime, this station 5.2 goes anoxic, and in September you get a fall turnover and it very rapidly reoxygenates. Anoxic reoxygenation, anoxic reoxygenation. This is the phosphate. The thing that annoys me, all right, what happens is, let's try to concentrate on the data for a moment. When the bottom goes anoxic, just look at the data, you get immense phosphorus concentrations. And as we saw yesterday from the diagenesis model, this is readily understood, okay, from Mortimer's day. The thing I want to look at is, you see that this phosphorus disappears. Look at this. We've got, I don't know, what is that? Well, I can't read the graph anymore, but when you look right here, this is now the bottom reoxygenating. These couple of data points right here. when you look at that bottom reoxygenating, the dissolved phosphate drops like a rock. Here, you know, when you look at the bottom reoxygenating, that dissolved phosphate drops like a rock. And you can even see, look here, if you look really carefully at the data points, I think it goes up, the oxygen goes up and comes down again for a minute. You know, the phosphorus, when the oxygen goes up, it comes down and it goes back up again. So when the bay reoxygenates, that phosphate disappears. And the theory is this is co-precipitation with iron. What's happening is that when there's dissolved iron in the water column, when the bay reoxygenates, that iron sorbs the solids. It becomes a particle again, and the phosphorus sorbs to that. So this is co-precipitation. Fair enough. I'm annoyed. I'm annoyed, as you know what, that nobody worries about this or looks at this or has investigated this, but it's inarguable. I ran this past Jay Taft, if you remember Jay Taft. He liked the idea. That was a long time ago.
Yeah, but I guess the sediment flux model would start to draw it down, but it may not draw it down quickly enough is the problem, right? But the sediment, you know, the sediment flux model in the real world too, not the sediment flux model, but in the real world, when you get that aerobic layer and the iron oxides get reduced, then you're also releasing iron from the sediment. So that is also your source that co-precipitate and go back down. But at one point, and this is a long, long time ago, we used to call it CTAM. Remember, I think you had it in your models. So you've given that up, I guess.
Yeah, and I've tried putting it back in, and I've ran out of time in this endeavor. But okay, so what we do is we've got to, you see this dropping precipitously, no precipitous precipitation, no pun intended. But in all seriousness, what we do is we have an empirical PO4 settling rate that we enact in anaxic portions of the bay in like September. Because if we don't get rid of that stuff, it stays in the water column for a long time and sort of corrupts our model calibration later on. So I'm glad you mentioned that because I wanted to mention it and forgot. And like I said, I had that graph there. It must have been a reason, right? So in any event, this is settling rate of precipitated phosphorus. It's an empirical number. It's just there for like 4 weeks or something when the bay turns over. And we only enact it where the bay is anoxic because that's where the iron comes out and that's where the precipitation will occur when the bay reoxygenates.
I wonder if you tried it, if you increase the aerobic layer partition coefficient, because you don't have to worry about getting too much phosphorus out because there's a limit to what's there, but increasing the partition coefficient,
sorb it back up,
just sorb it hopefully back up a little bit quicker. I don't know. That would be an interesting test.
Interesting experiment. Okay, let's see. We're going to break in a couple of moments. I don't want to belabor this, but once again, just as with the this equation for dissolved organic phosphorus is analogous to the equation for dissolved organic nitrogen. And once again, it's up to you to specify the fraction of metabolism that goes to dissolved organic and the fraction of predation that goes to dissolved organic. And so I think, okay, so that concludes the phosphorus lecture. And I guess, I don't know how long I've been up here, but I see yawns. So let's all get some coffee and some sugar, and we'll come back in about 15 minutes, okay?